Good morning, everyone. My name is Marco Russo. I'm here today after the party, first session in the morning, to talk about Scalable BI and advanced modeling with Microsoft SQL Server analysis services and Power Pivot, which means that fundamentally this is a session level 300. Just to set your expectation in the right way, I'm going to talk to several topics that will be familiar to those of you that have some experience with Power Pivot or with Analysis Services Tabular. How many of you already created models with one of these tools? How many Power Pivot? How many Tabular, Analysis Services Tabular? How many of you never used these tools? Just someone. Okay. For those of you that don't have a particular experience, there will be some information for you. Most of the content of this presentation comes from experience we had in the real world implementing solutions with our customers. And I will try to give you an idea of what you can do and what you cannot do with this platform today. This is going to change in the next release of SQL Server, of course. So even if you will not get some detail about certain particular information I will give, try to get the big picture from this session. As I said, my name is Marco Russo. I'm a consultant in business intelligence. I don't work for Microsoft. I'm not a Microsoft employee, even if I work mainly with Microsoft technologies. So my point of view is, is a little bit with a little bit of distance from the platform. Sometimes I'm critical about the platform, but in this case, I can say that the engine of analysis services, Tabular, is very, very powerful. Sometimes it is not well understood, and today may require some optimization, as I will show you during this presentation. So, this is the agenda for today. The session will be pretty dense, but I will try to get 5-10 minutes at the end for some Q&A. This is the list of the topics that we are going to see. We will start with some consideration about the data modeling, but we will spend most of our time about performance. Because if you think about how to scale, probably we need to scale out, scale up, and we want to understand what are the limits and what are the right tools to use, and actually what worked and what didn't in the real world. Just to explain some difference, we have two products with the same engine. Actually, we have three products with the same engine, because today we also have Power BI Designer. We have Power Pivot, we have Analysis Services Tabular. However, Power Pivot and Power BI Designer are in the area of self-service BI, whereas Analysis Services Tabular is more for corporate BI. But the engine is the same. There are a few differences in the features of these two products. In particular, in Power Pivot, you have today synonyms and linked tables, which are two features that are only in Power Pivot, whereas in Analysis Services Tabular, we have security roles, partitions, incremental updates, and the ability to define the segment size processing large tables. As you can understand, this is for corporate BI. Security, role-level security for the users, and a few features that are very helpful when we have databases that are in the order of magnitude of a few gigabytes. When you have 100 megabytes of database, you will see not many differences in performance and in how to manage things between the two products. So these two products have a common engine. This common engine is Vertipack. Vertipack is, the real power behind these products. And the idea is to store data in a different way. Vertipack is a column store, is a columnar-based database, and is an in-memory database. So it merges two technologies, organizing data by column and keeping data in memory in a compressed way. How it works. Let's start with defining what is a raw storage layout. A common relational database, Oracle, SQL Server, Access, works usually in this way. You have a table, and data of the table is stored row by row. For example, in SQL Server, you have an allocation unit which is 8 kilobytes, and SQL Server tries to store as many rows as possible in one page. However, even if you use compression, all the values of all the columns of one row are next to each other, are in a contiguous area of memory or of disk. So you store data page by page and row by row within a page, which means that when you have to get one value from one column, you have to read the entire row and probably the entire page that contains several rows. When you create an index in SQL Server, what do you do? What do you do, really? You create a copy of the table, which has a smaller amount of columns, and so has a higher density per page, which increases the performance even when you have to do a complete scan of the table. So we are so used that this is the natural organization of the things that you, especially if you come from a relational world, you may not think that there could be an alternative to that. And the alternative is the columnar storage layout, which means that we store data column by column. Imagine, for example, for a moment, to create a file on your hard drive, and each file contains only one column. In each position of this file, you have the value of that column for a particular row, which means that if you have to retrieve all the columns for a particular row, you have to open many files, access to several positions in these different files, and merge data together. Very expensive, more I/O operations. Not good if you have to do operation row by row, but when you have to scan an entire column, for example, you want to sum the balance, from this column you have to scan only one file in memory. One file on hard drive. Now bring these structures in memory, and you have array in memory, which are in a sequential way. Scanning memory in a sequential way is way faster than accessing memory in a random way, which seems strange, but when you go down at the hardware level, there could be a difference of 1 or 2 orders of magnitude. And this is the difference why Vertipack is so strong. So Vertipack uses this organization in memory using compression. What does it mean? Data are compressed. And when you have, for example, data for a column, imagine you have the quarter column in a date table, and you have quarter 1, 2, 3, 4, and nothing else, because you have only 4 quarters. So chances are that you have several contiguous rows with the same value. And the compression that Vertipack uses store data trying to reduce the number of rows and writing, for example, only Q1 start at row 1 and is repeated for 310 times. The same for Q2 and so on. Now, you have to store one table, not just one column. So the second column, if you imagine that you sorted the table by quarter, the second column will not have an optimal sort order because you would have product 1, 2, and then again 1, 2 for the quarter 2, and so on. However, if you have a good sort order, also the other column might have a compression resulting from this approach. This technique of compressing data is called run length encoding. However, there could be columns, like, for example, the price, which have different values for every row. And in this case, this optimization is not applied by Vertipack. Now, Vertipack does this automatically. And one thing that has to sort the data of your table in order to retrieve in a heuristic way the best possible optimization. This is done automatically by the engine. But why I'm speaking about this? Because if you know the basic principles of how the data is compressed in memory, you can think about what are the right columns to show to the engine in order to obtain the better compression. And as you can see here, having a column that has a unique value for every row is not a good idea, because it will not be compressed very much. And do you really need this column for your analysis? Probably not. Probably you don't need a unique ID in your fact table. You need this in your fact table, in your relational database, but it's not a good idea to bring this table in memory in Vertipack. So this technique is merged with another technique, which is the dictionary encoding. If you have a string in a column, this string is not stored repeating the same string many times. We have a dictionary that contains a list of the values. I talked about strings, but it is the same for a floating point value. And in the column, you only have a minimum number of bits that represents the index to the dictionary. In this way, we reduce the amount of RAM that is required to store each row in memory. The two techniques are merged together in Vertipack, and so the X velocity in-memory engine, which is the official name, the marketing name of Vertipack, which is the internal code name of this engine, these two techniques are important in order to obtain the maximum performance. Because if you reduce the amount of RAM, if you improve the compression, data is stored in a compressed way in memory, and when you query your tables, Vertipack always scans the entire columns that are involved in the query, and having a smaller amount of RAM to scan increase the performance. Vertipack leverages the current hardware. As we will see at the end of the session, choosing the right hardware is critical to obtain the maximum performance in analysis services tabular. So I provided you this initial information just to enter into the first topic of the session, which is, okay, we want to create a scalable solution. Because we know how Vertipack works, we can try to optimize the memory usage, because all the data of our database are stored in memory, in RAM. So we need large servers with a large amount of RAM. We have to improve the usage of the memory, and the first technique is we have to reduce the columns. If we have a column that contains a timestamp, or the user that made the last change to this row, maybe that we don't need this information in our analytical system, and we can just remove this column, because by removing a column, we save space. If you know how the tabular model works, you know that you can create calculated columns, which are persisted in memory, with a calculation already done by the engine at the process time. However, storing a column could be expensive, depending on the number of unique values that you have. But another reason is that Vertipack consider the data that you have in your table in order to obtain the better sort order to improve the compression. Calculated columns are evaluated after the compression has been made for the first columns, for the physical columns of the table, which means that calculated columns do not participate in making a decision about how to choose the sort order. And the compression you obtain for the calculated columns is not the optimal one. So in a large table, billion of rows, calculated columns are never a good idea. If you have a table that has 10,000, 100,000 rows, calculated columns are not a problem. But when you have 100 million of rows or more, then calculated columns should be evaluated carefully. Another important thing, reduce the distinct counts. When I approach a customer and the customer says, oh, we have 20 gigabytes in our database, I don't care. We have 2 billion rows in our fact table, 10 billion rows in our fact table, I don't care. But when I know that they have 30 million of unique customers, I'm worried. I'm worried because 30 million of unique customers means that somewhere there will be a column, customer ID, that has 30 million of unique values. And the number of unique values is critical, because a column that has more than 2 million rows, 2 million unique values, is a column that can present some challenge in performance. Not just for the distinct count, but most for the relationship between tables. But I will talk about this later. So when you evaluate to use tabular, the first point of attention is what are the columns that have the higher number of unique values. And the problem is that when you ask to a DBA, usually they don't know that. They just never cared about how many unique values you have. What is the distribution of the data? This is something that usually people doesn't know unless you are very aware of the data model. In your model, you might have objects that have a cost. So you create a data model in tabular. Data model in tabular has tables, relationships, columns, measures, and so on. But what has a cost? Obviously, you import a table, you import columns. Columns have a cost. But remember that also relationships between tables have a cost, and hierarchies have a cost. Because in order to create relationships and hierarchies, the engine has to create additional structures in memory, that will be saved also on disk, that will consume memory. And the memory, the RAM, is a limited resource. So you have to think about, do I really need this relationship or not? I'm not saying don't create a relationship just to save memory. I'm saying don't create too many tables with too many relationships. Star schema is good. Snowflake schema not so good because you have more relationships, for example. So this is something that you have to be careful about. Now, how can we understand how we are using the memory? So let's start with the first demo today. When you have a database, you usually have something like this. You have SQL Server Management Studio, or you may have Power Pivot in Excel. Now, if you have Power Pivot in Excel, you probably have a file on disk, and you know exactly what is the size of the file. But when you have Analysis Services Tabular, you might want to see what is the size of the database by going here and, for example, clicking on Properties, and you can see here that you have a total of 13 gigabytes. So this database is 13 gigabytes in RAM. Okay, yes, nice, but how this RAM is distributed? You have a few data management views that can provide you some information. However, Casper de Jong, that I don't see here, but he created a nice report in Power Pivot. So he created an Excel workbook that has Power Pivot model behind that simply query this data management view. So if you take a look at this, at the definition of this table, you simply have a select star from discovery object memory usage, which is the data management view that provides you information about the object that you have in memory. Now, by creating a few measures and calculated columns, he was able to create a hierarchy that allows me to navigate into my data, and I can see in this pivot table how my memory is distributed. So I can see that my audience database here has 13 gigabytes. If I drill down, I can see how the memory is distributed across the objects in the database. And as you can see, most of the data are consumed by columns, and I have a small amount of RAM consumed by hierarchies and relationships. So in this case, we already made our job. We already made our optimization, lowering the amount of RAM used by these objects. But as you can see, even if the fact table I have here is a fact table that has 4 billion rows. However, even if I have 4 billion rows for all the columns, the size of each column is different because of the compression, because of the dictionary, because of the distribution of data. And as you can see, ID time is a column that contains 7 gigabytes, that requires 7 gigabytes of RAM, whereas the ID date has less than 1 megabyte. Why this difference? Because this date is the first column used in the sort order, and fundamentally has the same value for hundreds of maybe thousands and thousands of rows. You always have the same date. You have date and time in 2 different columns. So as you see, we don't have date time in a single column because this would increase the number of unique values every day. By separating date and time, we already optimized the model. So this is an important tool, BISM memory report. You will find in the slides a few links to download this tool. And this tool is important to get memory about the objects that you have in memory. So I try to provide you a few information that will help you in evaluating how to improve your object, your model. Sorry. Okay. Next topic: improve data model. As I anticipated before, when you design a model in Tabular, you fundamentally have tables, relationships. You can have an approach similar to a relational database. However, a complete normalization of your database is very, very bad because having too many tables means that you will have too many relationships, which means that you will not have a good user experience. You cannot create hierarchies across different tables, and you may have to spend too much time navigating into relationship. You will not do that in your formulas, but the engine will have to do that. So there is a usability point and there is a performance point. But talking about performance, another important issue is creating natural hierarchies. What does it mean? if you have a model that has a year, month, day hierarchy, you know? Year, 2015, 2016, and so on. Month. How many months we have in the column month? We will say 12, because in this way we have a lower amount of unique values, which is a good thing for the compression, and this is true. But when you will use this model from an MDX client, for example, the pivot table in Excel. The pivot table in Excel runs queries in MDX. The engine of analysis services tabular that executes an MDX query over a tabular model has to do some job for the hierarchies. And when the hierarchy is not a natural hierarchy, you may have some issue with the current version of analysis services tabular and of Power Pivot. Which means that it is a much better idea to create a natural hierarchy. What is a natural hierarchy? Simply said, instead of having 12 months, I should have 12 months for every year. So that every name that you have in a hierarchy has always only one parent. So January 2015 will have 2015 as a parent, and January 2016 will have 2016 as a parent, instead of having a single January that could belong to 2015 or 2016. This is very important. This is not highlighted very well in the guidelines provided by Microsoft. Actually, I haven't seen any of these warnings in any official document, but this is an issue that when happen, you are in trouble, because you see that in certain combination of query, the performance are very bad. There is a link in the slide about an article that describes this problem very well. So this can affect also a small model. Size of the model is not important. When you design a date table, you have to make important decisions. And I'm always a bit scared about Microsoft saying, oh, we are going to release an automatic generation of date table, because this would be good if they follow the best practices. And one of the best practices is using year month for the column that contains the month. Why? If I merge the year and the month, for example, in Power View, I have a better UI. In Power View, you cannot combine two columns like year and month in order to create a line chart. So if you want to see a line chart for more than 12 months, you need a single column that has both year and month, because otherwise you will see only 12 months and you will not be able to see different years in the same chart. Also in this case, this is more about data modeling. There are not many performance implications. DAX queries are not affected by the problem of the hierarchy that I mentioned in the previous slide. This is the problem that I mentioned is only for MDX, but this problem of the smart columns is for the DAX and the DAX clients, like for example Power View or the new Power BI, same problem. And if you want to improve the experience of a user that connects in Power BI, another thing that you have to do is provide synonyms and Power View metadata in your model. What does it mean? Let me show you a small demo. Just prepare here. And I explain you with some example what I mean with this. This is a very simple data model that I have in Power Pivot. Now, I have actually Excel tables just to show you in a larger way, but you imagine you have a list of customers and a list of vehicles. So when you create a data model in Power Pivot for this thing, you will obtain something similar to this schema. So you have two tables, a relationship between these two tables, and you can populate these two tables with a lot of data, and then you can upload this table to Power BI. Now, Power BI has a nice feature that is Q&A. Let me show you this. So with Q&A, I can ask a question to my data model. And when I ask a question, I can ask show vehicles. Now, many people may be used to use this term, but you may use a synonym for this term. You may use cars. You may use other terms. How can the engine know what is the right translation? How can the engine know that if I write car, I mean vehicle? You may think that the engine has this knowledge embedded because of the knowledge of internet. But in reality, your specific domain model may use each name in a specific way. So it's better if you embed this knowledge into the data model. So when you create a data model and you want to offer a better user experience, in Power Pivot today, you have this button, Synonyms, that allows you to specify for each table and each column which are alternative or additional names that can be used in Q&A. So the only goal of providing this information here is to increase the usability of Q&A in Power BI. And I can show you an example in this other model where I already created my synonyms. And as you see here, I wrote car. There are many other details. You can also specify verbs or other things that are today not available in this UI, and I hope they will be available in the new Power BI preview very soon, because fundamentally this is an important part of refining the data model. If you don't use synonyms, at least use meaningful names in your tables and columns, because this is important to provide a good UI, a good user experience, and a good UI to your user. Oops, come on, okay. So when I do this, I can obtain a better experience here. So for example, if I show Marco car, as you see, this has been translated in show Marco vehicles. And so the relationship of ownership between the two tables that is created by the relationship is automatically inferred by the data model. So also having the right relationships in the data model is important for Q&A. This is why I'm saying this in a session about scalability, because yes, scalability is important, but don't forget usability. When you create a data model, decisions that you make about table names and column names are here to stay. And it's better if you spend some time at the beginning providing the right names. Don't use these acronyms or something that you only know, or prefixes for the column names. Don't use anything of that, because otherwise you will have a very bad experience here. Or you will have to spend a lot of time providing synonyms for all the columns. So starting with the right data model is certainly better from this point of view. Okay, I can go back to the slides. Now, we introduced the problem of having a data model in memory. We have to optimize the memory. We have to increase the compression. We have to provide a better UI. But when you approach a large amount of data or a large number of users, because scalable means scale up and scale out, the first problem that we have to face is to optimize DAX. Why? Tabular doesn't have aggregations. Tabular doesn't have indexes. Tabular always scans the data that you have in memory. And even if the data are compressed, there is some job to do. And the job that is created by the engine, that is performed by the engine, is generated depending on the query plan. If you think about SQL Server has a long history of query plan optimization. So the engine generates query plans that are very sophisticated. Tabular doesn't have this history. Tabular debuted 5 years ago, and we still don't have a sophisticated engine today. Probably the next release of SQL Server and analysis services will have a better engine. We already have a better engine in Power BI Designer and in the preview of Excel 2016, but we certainly are not where SQL Server is in terms of advanced analysis of the query plan. What does it mean? the way you write your DAX measures, the way you write your DAX query strongly affects performance. You may obtain the same result in 5 different ways, but the performance are different. And so you still have an impact in the way you design DAX, which means that usually the only way you have to optimize a model is to optimize the DAX code. It could be a challenge. It could be not easy. You have to learn how the engine works and how to read the query plan, how to read the information that the engine can provide you. So there are many information that you have to know, but these days we have some tool that we can use. How it works. When you run a query to analysis services or to Power Pivot, the engine receives a DAX or an MDX query. Regardless of the language, a query plan is generated if you work in memory. There is another option, which is direct query, which we don't consider in this session. In direct query, your DAX query is translated into a SQL query, and the engine is SQL. So you can do all the optimization that you want in SQL. But if you want to get the real performance benefit of tabular, you have to go in memory. And when you work in memory, the Vertipack storage execute the storage engine queries and provide the information to the formula engine that solve the query. So this is the area that we analyze. In this area, we have 2 engines, the formula engine, the storage engine. Talking about this, I could talk 2 or 3 days just describing what these 2 engines does. But fundamentally, the idea is very simple. The formula engine understands DAX. Analyze DAX, creates the query plan, and ask to the storage engine, please give me this column. Give me this column aggregated by this other column. So the storage engine handles very simple operation in a very fast way. The formula engine has the knowledge about more advanced and complex formulas. For example, if you ask for the top n, or you ask for certain joins, probably only the formula engine can do that. But when you ask, give me the sum of this column divided by year, the storage engine can do that in a very fast way. The storage engine works in using many cores of your hardware, whereas the formula engine today is still single-threaded, which means that we have to understand how to optimize DAX. First of all, understanding whether we are stressing the formula engine or a storage engine, and then we have to use different approaches, optimizing one or the other. How can we obtain information about these counters? We have a tool provided by Microsoft, which is the SQL Server Profiler. The SQL Server Profiler is a general-purpose tool that provides you all the information about the events that happens in the engine. But spending time retrieving the data that we really need to optimize a query is expensive. We usually spend more time just to filter the information that we need. So with the help of several people in the community, today you can use DAX Studio, which is a free tool, open source tool that you can download from Codepex. I will show you in a minute. And DAX Studio fundamentally gets the same events that the SQL Server Profiler will show you, analyze these events, and provide you a synthetic information about the performance analysis that you can use to optimize the DAX query. DAX Studio does not optimize the query for you, unfortunately, but will help you to spend less time getting the numbers that will make you able to decide if you have to optimize the query, looking at the formula engine, the storage engine, using one approach or another. Another interesting tool that I will show you is the OLA pivot table extension. Because in reality, even if you create a tabular model or a Power Pivot model, most of the times you will still use a pivot table in Excel to query this model, and the pivot table generates a query in MDX. So it could be nice if I can grab the query generated by Excel in order to quickly analyze my performance. So let me show you what are the tools and how we can use these tools to analyze the performance. So first of all, I want to show you DAX Studio. So DAX Studio can be downloaded here from Codeplex. You can download also the source code. You can participate to the development if you want. But if you are lazy, you just download the executable and you obtain this tool. Now, this tool has, imagine SQL Server Management Studio just for DAX, and in this case also MDX. In this case, I prepared in advance a DAX query just to show you a couple of things. In this case, I have a DAX query that is particularly slow. I ran this query before. This query required almost 25 seconds to run. And I have here, in the lower part of my window, a few information. One is about the query plan that I will see in a minute, and the other is about server timings. I usually start from here. By looking at the data that I have here, I can immediately see that the time, the 26 seconds I waited were spent mostly in the formula engine. Formula engine, storage engine. So without having to look at all the details of all the events, I already know, oh, I have a formula engine problem. If I have a formula engine problem, it's relevant to take a look at the query plan. Now, the query plan could be long, but if you see here this records column, we extracted a number that defines the iteration performed by the formula engine. When you have a slow running query, usually you have an iteration over a large amount of rows. In this case, we are iterating over 67 million rows. Now, the original table has only 60,000 rows. How it is possible that we are iterating millions of rows? Because we have in the query two nested loops that are creating a sort of cross-join. And this is the reason why this query is so slow. I can also quickly take a look at where is my bottleneck by sorting my list by records, and I see, oh, look, there is an operation here that is slow. Now, how to understand what is the operation slow, that's another story. I will require 2 days. But I just want to show you that instead of spending 10 minutes to locate that the problem is the formula engine in a particular loop, I obtain this information in a few seconds. Now I can try to write my query in a different way. So this was the first query, 30 seconds. Now I run this query. I run this query again. The database is the same, but as you see, this time the query runs in only 1 second. So I already writing the query in a different way. I optimize the query. As you see, I have a total time of 1 second, and 99% of the time is still in the formula engine, but I optimize the formula engine. Now, by looking at the formula engine, I repeat this operation. I see, oh, look, I still have an iteration over 1 million rows. I know that I have 60,000 rows. Maybe I can write the query in a different way. So I try to do the job of an advanced query engine optimizer should do. And I rewrite my query using a different approach that reduces the number of iterations. And when I run this query again, I see that the time spent by this query is now 91 milliseconds. And again, the reason is that I obtained here a lower number of iterations. And if you are not satisfied, at this point I would suggest you to stop the optimization because you are already under 100 milliseconds. It's good enough. But just as an exercise, if you want to optimize this more, you can. The query is much more complex. The query runs 5 times faster. Nobody will see that unless you have 10,000 users. But when you have only 1 user, nobody cares. And scalability is a complex. And the reason is that we reduced this. Now, if you, like me, did this optimization using the SQL Server Profiler, DAX Studio is just the tool to use just for how it is to retrieve this information without looking at many different places in the SQL Server Profiler. So, okay, this was a DAX query. But in reality, I have a different story. The real world is different. The real world is this. I have Excel. I have a pivot table in Excel, and I'm running a query over tabular. When I run this query over in tabular, I'm using Internet Total Sales, which is a measure in DAX. So I designed the measure in DAX. I probably had to optimize the measure in DAX, But the measure in DAX is run in an MDX query. And my DAX measure is low only in this pivot table. So my first problem is to reproduce the condition where I have the slowness of the measure, because maybe that I'm not able to reproduce the problem in DAX. So first, I have to retrieve the MDX query. You can run the profiler, look at the events, blah, 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 or you can right-click and go here in the OLAP pivot table extension. OLAP pivot table extension is another free add-in that you can download from Codeplex. It's an add-in for Excel that enables you to get, that provides you many, many useful features, but the one that I want to use is this. I want to see the MDX query generated by Excel for this pivot table. That's it. Now, I copy this query, and DAX Studio, despite its name, can get an MDX query and can run an MDX query, because the target is tabular. And by running this query in MDX, it provides me all the information about query plan, server timings, all this stuff that will enable me to understand where is the problem. Now, wait a second, Marco. What if I want to change the DAX measure and I want to try if my change will work? I have to go in Visual Studio, I have to deploy the measure, I have to wait a lot of time because Visual Studio is slow, blah, blah, blah. No. You can use a better way. You can do this. MDX syntax allows you to define a local measure, also in DAX. The syntax is with measure, and you write the DAX measure. For example, my MDX query was using this measure, Internet Total Sales. This is the MDX syntax. But in reality, what is Internet Total Sales? Is a measure defined in the Internet Sales table. If I write the same name here, I override the definition that I have in the model, and I write my own definition of this DAX measure locally to this formula. So I rewrite, at the beginning, I just copy the same definition, the same DAX measure from my data model, and I run it. So I can run this, it works, I have all my events, my query plan, and my result. At this point, I can try to optimize the query. The point here is not to optimize the query, but just to show you that if I change something, this change that I apply to my formula immediately reflects in this result, and, of course, also in the performance. Once I fixed my formula, I solved my bottleneck, I copy this formula in Visual Studio, I do the deploy, and it works. I can save 1, 2, 3 minutes for every iteration by just using this technique. So I think it's important to share this with you. Finally, we have seen a problem with the formula engine. However, and this is something that is important to me for the next part of the session, what if I have a problem in the storage engine? Remember, you have seen in my computer I have a table that is 4 billion rows, a fact table 4 billion rows, and it requires 13 gigabytes of RAM. When I run something like that, for example, I have a simple formula that runs a distinct count over a column of the audience table, 4 billion rows. What is going to happen? I want to show you, with the task manager open, what's happened when I run this query. So I cleared the cache before, because of course I want to run this query with a call cache, and clear cache is just a button in DAX Studio. When I run this query, I can see that all my CPUs goes 100%. Scalability, many users think about this. And I can see here a few useful information. For example, I can see here that I waited for almost 4 seconds. But in reality, I spent 27 seconds of CPU because the query used all the cores. If I had double the cores, probably I would have spent less than 2 seconds. Unfortunately, there is a limit to that. This scalability works well when you have all the cores in one socket. As we will see soon, If you have more sockets, it doesn't work so well. And most important, 99% of the time has been spent in the storage engine. When you face this problem, the optimization technique is completely different. When you have a formula engine problem, you have to change DAX. When you have a storage engine problem, you may have to change the data model, the compression, sometimes also DAX, but usually the problem is more complex. So this is another important tool that I use. Of course, again, what are the techniques to optimize that? Long story. But I want to show you that if I do the same on another column, for example, look at ID time. We have seen weight, which was a column that has a particular number of unique values. If I repeat my operation here, the table audience has always 4 billion rows. So technically, in SQL, this will not be so different. But in this case, you see that this query ran in 2 seconds, so half of the time. Why? Because of the different number of unique values, different distribution of data. So the performance depends on many things and could be different column by column. So don't consider for tabular the rules that you consider good for SQL Server, for example. This is a completely different story. But again, the important thing is that I can focus on different techniques of optimization depending on formula engine or storage engine. You have to spend time understanding the meaning of these numbers, and the tools is just something that will help your productivity getting these numbers in a faster way. So, just a quick recap. We have seen that we can create a model. We have to optimize the memory. We have to optimize the DAX code when it is necessary. But as you have seen in my last demo, how can I improve the performance of this query? If this is my data, I already made all the compression. I already made all the optimization possible in DAX. And my query still runs in 2 seconds, going 100% of the CPU, my entire server. Ooh. Well, there is the cache that can help me, but fundamentally, how can I improve? If 2 seconds is too much, what can I do? Scale up. What does it mean, scale up in this case? Let's take a look. Fundamentally, the hardware is important. And the performance of my query depends on the hardware. So before starting making consideration about the hardware, we can start making consideration in what is the size that we can handle with Tabular. Fundamentally, the more data I have, the more time my scan will require. So if I plot a line, I can say, well, if you have a table, your largest table has 10 million rows, the time required to scan 10 million rows in memory in a compressed way is so small that whatever error you can do doesn't matter. It will be fast. Life is good. 10 million rows, you have to invent something really strange to see a slow query with 10 million rows. Okay, let's go into a larger area, 100 million rows. My fact table is 100 to 100 million rows. Not bad. Usually it works well, but be careful. You might have to optimize DAX. If you write DAX not in a good way, you may see that, oh, you use a filter in this way. If you use calculate, it's better, something like that. So minimal optimization of DAX, problem solved. It works. When you approach 1 billion rows, I know Microsoft shown, the first time they shown Power Pivot Tabular, oh, 2 billion rows fast. It's true, with a sum of a column. Try to do something different. Try to do something more complex. Try to write a more complex calculation. You might see some difference. And at this level of performance, this level of size, usually you have to start worrying about the compression. I mean, when you have 100 million rows, with a modern hardware, 2, 3 gigabytes of RAM is enough, usually. You don't have to worry too much. But when you have 1 billion rows, every byte you save is 1 gigabyte. So the compression is important at that point. Because reducing memory means reducing the time to scan the memory, which is important. And another important fact could be the segment size. In tabular, you can define how many rows are processed segment by segment. Why this could be important? Because the internal compression, the internal reorganization of the rows in order to obtain the maximum order is done segment by segment. So if, instead of providing 8 million rows, which is the default, when you have a very large table, you may increase this number to, I don't know, 32 or 64 million rows, which will require more memory during the process, but will produce a more optimized fact table. We have obtained very good results by doing this type of optimization. But we want to go, we want to go at a higher level, 10 billion rows. When you reach 10 billion rows, 10, 20, 30 billion rows, I will show you a slide in a moment. The problem is that if you expect your user to drill down in a pivot table and immediately see the result, we may have some issue. Because even with the best hardware you can buy today, the scan time is easily in the 1, 2, 3 seconds, which is not acceptable for an end user in a pivot table. So what we can do at that point, strange optimization. We introduced the concept of aggregations again. How many of you worked in multidimensional? Okay. I will show you one technique, still, but it works. Today, I think that if you have 100 billion rows, tabular is not a good idea. I mean, you have to reduce the number of rows. That's the problem. I don't see a way to solve the problem because you just don't have a machine that can store all the data. The problem is that you don't have enough RAM in a single server to store all the data. That's the usual problem that you have. Not to mention that also the performance would be slow, because if you have to wait 20 seconds for a query, it's not good. In this slide, I show you what is the typical scan time that you can have in the storage engine. As you see, 10 million rows, 20 milliseconds for a complete scan of the table. Do whatever you want. It's fast. Unless you create a problem in the formula engine, the storage engine is good. But as you see, 100 billion rows means that you cannot wait less than 10 seconds for a single storage engine query, and a single DAX query may run several storage engine queries. So probably is too much with the current hardware we have today. And one of the problems is that we still cannot scale out, but I will talk about this in a moment. So why I'm saying this? Because my intention is to be able to drill down in a pivot table and get an answer in less than 2 seconds. That's my goal. And to reach my goal, you see where are my problems. 10 billion rows is usually the limit I can have today. However, the size of the fact table, of the largest fact table, is not... What? I don't understand. Oh. Sorry. I should have clicked something wrong. This one? Better. Okay. So, I say that the size of the fact table is not the single most important concept. Another important thing today is the size of the largest dimension. Why? Because when you have, for example, you have the customers, and I'm from Italy. I work with companies all around the world, so in both the United States and in Europe. And usually in Europe, we don't have problems because normal companies in Europe have 1, 2, 3 million of customers. And it's good. Life is good because we don't have problem with tabular. In the United States, Medium companies, especially in healthcare, have 10, 20, 30 million of customers. And this is a problem because when you have a large dimension, which means you have a relationship between two tables that has more than 1 million of unique values through the relationship, you may start to have some problem. And the problem is the way the engine works doing the aggregation, transferring the list of the customer. When you group, for example, by mail, you get 15 million of customers, of customer ID, that are transferred between two tables. And this operation is not exceptionally fast. The new engine is much better. In 2016, we will see improvements. But today, this is something that is a problem. So having 100 million rows is not a problem in the fact table. But if you have 100 million rows in the fact table and 10 million rows in the dimension customers, I'm not saying that this is a problem that you cannot solve. I'm just saying you will have to adapt your data model in order to do some optimization at the data modeling level. So it's better if you have smaller dimensions. And the technique to optimize that is to create dimensions for the common used attributes that will have a lower granularity. This is the idea. So in a simple model, we have this. We have, for example, in this case, I have products. I have 10 billion rows in the sales by product and 1 million rows in the product table. OK, that's fine. In this case, 1 million rows in the product table, I don't do particular optimization techniques. I keep this data model. But if I see that with 10 billion rows and 1 million rows, I start to see some issue, I can consider doing something like that. I can try to optimize the dimension granularity, which means most of my queries will be by category and subcategory, for example. And I will not always do a query at the product level. If I want to obtain a better optimization, having this virtual relationship will help me, because I can have an aggregation here and a relationship that has a lower number of unique values, which helps the performance a lot. So at this point, you can also do another thing. If I know that most of my queries will be done at another granularity, what I can do, I can duplicate my fact table, and I can create my aggregated fact table that instead of having a product granularity, has a product subcategory granularity. I can obtain this table as a result of a DAX query over this table, if you want. And the interesting idea behind this is that I can reduce the order of magnitude of my fact table. So I solved two problems. Here I solved one problem is the size of the dimension, but the other important problem is the size of the fact table. If I start to have performance issues because of the size of the fact table, I can consider having another fact table that works at a different granularity level. Doing this optimization actually works, but there is a challenge. Don't do this if you don't really need this, because the next stop here is how can hide to the user the complexity of this data model, because fundamentally I have to query one table or the other depending on the attributes asked by the user, but the user don't want to see this complexity. Want to see product, measure, nothing else. You can do that by creating particular DAX measures that understand what are the granularity of the request and use one DAX expression or another, using one table or another, depending on the request. It's complex. It's not really easy to handle because there is another problem. If you start writing if in your statements, you have another problem, which is the formula engine doesn't like if statements, because the optimization, especially in a pivot table in NDX, is not very good. So there are many, many details to worry about. But if you go in this area above 10 billion rows or above 1 million rows in the dimension, I'm not saying that you cannot do anything. You can do something, but you need to work a lot on the data model and on the DAX level to hide the complexity to the user. We still didn't publish any white paper on this, but this is something that I hope to be able to document in a better way in the future, because it's something we worked a few months ago or just weeks ago. We are still waiting the customers going in production, but the results that we have until now are very, very, very good in terms of results. So in terms of scale up, I can optimize the data model when I reach a certain volume. What about the scale out? Where I can scale up when I have to optimize the performance of the query, the latency of the query, the database size. You want to scale out when you have two problems. Number of concurrent users. To give you a number, if you have 100 users that can access to the database, usually one database is enough. But if you have 1,000 users that could query the same database, at that point it's important to understand how many concurrent users you might have in a single, in 1 minute. And you have to evaluate the chances that the same query run at the same time. Because as you have seen, when the storage engine has to scan a table and uses all the cores, you have a problem. Fundamentally, you have one query running at a time. If you have two, they double the time. So in order to avoid the problem, we duplicate the database in different servers, and so we scale out. But the scale out is simply a duplication of the database with the same techniques that you can use in multidimensional. So usually we have a process server that runs the process. If you have a large database, the processing time could be very, very long. So we process the database, and we deploy this database in different query servers, so that different query servers will receive queries made by different users. This is the architecture that is fundamentally the same architecture that you can find documented for analysis services multidimensional. It works well also for tabular. I have to say that the tabular also work pretty well with the synchronization between servers. It's something that in multidimensional, many people don't use synchronization, but I have seen that for tabular is an option that you can consider because it's better than many other options that we tried. So if you have the scale out problem, the architecture is nothing new, same as multidimensional. But an important point is the hardware selection. How many of you runs the server in a host that you don't have control? So you don't know what is the hardware. How many of you? Well, many of you can control the hardware, which is a good idea, because the hardware is very important. The hardware is very important because most of the servers that you find in a server farm these days have these characteristics. The average of a server is around 2.4 gigahertz. But you can see a huge performance improvement if you go on a server that has a speed that is a clock speed higher than 3 gigahertz. 50% of improvements means moving from 1 second to 700 milliseconds just by changing the clock. Then add more cores. Increase the L2, L3 caches. Why the L2, L3 cache are important? Because the RAM is the other problem. Most of the servers have 1,300 or 1,600 megahertz of clock speed for the RAM, but modern servers can reach 2,000 megahertz. It's hard to buy a machine with this characteristic. You find very few machines that have these characteristics, but you can see the difference. Same model, different performances. But the good news is if you can choose the hardware, you can allocate your budget in a different way. Spend more in CPU, spend more in speed of RAM. Don't look just at the amount of RAM, look at the speed of RAM. Don't spend your money on disk, because disks are not used. When you run a query, there is no I/O at all. There could be I/O during the process. There could be I/O if you page during the process. But fundamentally, you have to keep the entire database in memory. And once it is in memory, there is no I/O. So disk is not important at all. And this means that you can spend much less for the disk. I want to give you an idea of how much this is important. Moving from a hard drive to a solid-state disk, just for the I/O, means moving from this order of magnitude of latency to this one. But look, the RAM is different than solid-state disk. If I go to the next slide, you can see this better. Your solid-state disk, which is fast, is much slower than the RAM. So the RAM, having data in RAM, means having a better access time. But the RAM is the new bottleneck. The RAM is the new I/O. Because when you have to scan a lot of RAM, having this column that you have to scan multiple times in the L3 cache is important. What is the problem of the 1 or 2 million unique customers? When you do a join between two tables, dimension and fact table, the list of the customer is something that is iterated often. If it can be stored here, it will have a lower access time. If it is too large that cannot fit the L3 cache, means that you have a lot of travel around RAM and L3 cache. So having a larger cache allows you to have a large dimension in your data model. A few CPUs today allows you to share the L3 cache across different cores, which means that you can raise from the typical 2 megabyte to 20, 30 megabytes of L3 cache shared across the cores. And again, L3 cache, L2 cache. But in this case, okay, there is a difference, but fundamentally is smaller. But as you see, the difference between the RAM and the L3 cache is an important one. So when you buy a server, usually the vendor will give you a number which is the sum of the processing power of all the cores. Unfortunately, for Tabula, this is not so important. The clock rate is much more important because a few operations are single-threaded, and so the clock rate is fundamental, especially for the formula engine-bound problems. And the other surprise, if you buy a desktop today, you spend less than $2,000. Usually with $1,000, you get a desktop that is faster than most of the servers that you have in your company. That's the problem. Because when you do the testing with your workstation, it's fast. As soon as you deploy, it's slower. And you think the problem. The other problem is that usually you buy an expensive server and it is slower because it has many sockets, many cores, is optimized for virtualization. And when you virtualize, having more sockets is good. For Tabular, is not good. Another detail, the E5 architecture of Xeon is usually cheaper and could be faster than E7. I made many tests with many customers, and we found that in certain conditions, E7 is better, but overall, E5 is much better because you spend usually half of the price, and you have comparable performance, if not better, in certain particular benchmarks. So if you have to buy hardware, think carefully. Don't just look at the specifications. Try to do some tests. Or look around. Maybe there is some blog post, I also have a few numbers, unfortunately, because if you publish a benchmark, then people will say, well, you didn't do this test in a good way, so I don't want to publish benchmark to make it too, it would be too easy to say this is not a good benchmark, I know. But, send me an email if you have some data, I have some number. I just don't want to make them public because it would be, it is not a very good benchmark. NUMA, when you have many sockets in a server, usually the RAM is local to each socket. The problem is that if you have a single database that requires 1 terabyte of RAM, and you have 4 sockets, each socket has 256 gigabytes of RAM, which means that when you scan some column, a few of these columns will be in the RAM that is on another socket. If your thread is running here and has to access the RAM here, you have to traverse this inter-socket connection, which is slow. Makes the access time to the RAM very slower. So NUMA is usually an issue. For the current version of SQL Server 2012-2014, it is much better if you force the execution of analysis services to a single NUMA socket. What if you have 2 sockets, 3 sockets? Don't use them, or create virtual machines, one for each socket, and use all the cores of one socket in one virtual machine. I know it's not an optimal situation. I hope that the next release of SQL Server will solve this problem, but today this is a problem. The only thing that we can do is trying to avoid the NUMA architecture at all, buying smaller machines and getting a higher number of machines. Certainly the problem is the maximum RAM that you can have on one socket is 700 gigabytes. I haven't seen 1 terabyte RAM with one socket today. So when you have a database that is 1 or 2 terabytes, you are in trouble because you will spend a lot. I mean, it works, but it is not as fast as it could be. That's the only issue. So this is the limit that we have today. As I say, the next release of SQL Server, I hope, will solve part of these problems. But today, we have to handle that. And the best thing is to allocate the budget of your hardware, putting money on the right hardware for what you have today. Virtual machines are good. The problem of the virtual machine is usually not the virtual machine by itself, but the fact that the virtual machine is running on a hardware that is very bad for tabular, because it has a low clock rate, has a low speed RAM, and maybe you have 2 different cores running on 2 different NUMA nodes, which makes things very, very bad. But when you allocate the virtual machine in a good way, on the right hardware, performance are very good. The virtual machine by itself does not affect performance in a significant way. So the virtual machine by itself is actually good, because if I have a NUMA machine, I use virtual machines to split the workload on different nodes in a very good way. So we have seen that we have to optimize the data model to reduce the memory usage and to improve the performance. We have to optimize DAX to improve the response time and to improve the scalability. If I reduce the workload on the storage engine, I can improve the scalability, the number of concurrent users. And you have to choose the right hardware, especially if you want to scale across 1 billion rows. Hardware is very important, but you will see the difference also with 100 million rows, especially if you have large dimensions. I have a bunch of links in the slides that you will be able to download from the Channel 9 website. However, if you want to get a picture now, and I think we have a couple of minutes for questions. Remember to evaluate the session. Evaluate the session. You are in a small number, so please evaluate the session, because below 10 evaluation, the session is not evaluated at all, so I invite you to do the evaluation. Question? No question. After the party. Okay.
How does SQL Server 2016 change some of the hardware selections?
Okay, the question is how SQL Server 2016 changes the hardware selection. Is too early to know. It's fundamental to know if we will have the NUMA support or not, because this will change everything. However, I can say that the clock speed will be still important, because the formula engine will be still single-threaded, probably. So I don't expect changes for that. Question?
For the things that you're talking about for Power Pivot, do those apply to Power BI Designer as well?
Yep. Okay, what I said about Power Pivot can be applied to Power Designer as well. Yes, a few features in Power Pivot, like synonyms, are not available in Power BI Designer now, but I think they will come in the next releases. Question? Okay, the question is about the usage of memory. Analysis services keep the memory, don't release the memory. It's a long discussion, but fundamentally, if you have large database analysis services, consider having a dedicated machine or a dedicated virtual machine. We can do something. We can discuss this offline, but usually, if you have large databases, dedicated machine is better. There was another question?
So I think we saw the session, like
Yep.
Power BI also used for the real-time analytics,
Yes.
as well as like here we can use with Power BI and give end-user access.
Yep.
And that scares me because they can run and we give access to do the ad hoc query. So is it just I'm too much worried about ad hoc query, or is just iterative process? You let them do something and then the performance issue, and then you have to change your data model and
Yeah. Okay. If I understand the question is okay, but having these queries could slow down the server. We have seen queries running on all the cores. Today, we don't have a tool to limit the resources used by a single query. We don't have a resource governor in analysis services, and I don't know if Microsoft is working on that. So we have to ask to Microsoft. These days, yes, this could be a problem. There are a few things that we can do in terms of timeout for a single query. And for example, what we usually do, when we have many users, we provide a few query servers to the user that cannot generate queries on demand. That uses usually queries that haven't been already made. The user that can generate any query will work on a dedicated server or a dedicated virtual machine so that if he does something wrong, he will not affect other users. Thank you very much. I think we are over with the time. Thank you very much. If you have other questions, I'm around. Thank you.